Hello, this is AP Chemistry, Chapter 3, Section 10 and 11. We're going to go over determining chemical formula from experimental data, empirical formulas, and molecular formulas. All right, so in order to determine the empirical formula of a compound, we have some mystery compound. So we don't know what elements are in there. We don't know how many. Usually it's binary, meaning there's two different compounds. But it doesn't have to be. So what we're trying to do is figure all of this out from the data that it's going to be given. So they're going to give you either percent or grams. If they give you percentages of elements, let's say X and Y, you're going to change it from percent to grams. Okay, we're going to see how in a second. Then the next step is to change it from grams to moles. So we're going to convert grams to moles using our value of the moles. We divide by the molar mass for step 2. Step 3, divide all of the moles that you get in step 2 by the smallest answer. And then step 4, multiply those answers to part 3 until you get whole numbers. So we got to do some examples so we understand what is going on. So in this example, 3.18 from your textbook, we have a laboratory analysis of aspirin, and it determines the following mass percent composition. So we have 60% carbon, 4.48% hydrogen, and 35.52% oxygen. Okay, and the problem says find the empirical formula of aspirin. So using these percentages, we need to get all the way down here to the empirical formula. So we're going to change percent to grams. I'm going to do it over here again by hand. So step 1 is to change those percentages to grams. So what we're going to do is we are going to assume that we're starting with, this is 3 different elements, so let's call it X, Y, Z. Okay, and really it's C, H, O, and we're trying to figure out the little subscripts down here. How many of each element do I have? So if we assume that we have 100 grams of this aspirin, and if I have 100 grams and 60% of that is carbon, that leaves me with 60 grams of carbon. And it's 4.48% hydrogen, so that means I would have 4.48 grams if I had 100 grams of my sample. 4.48 grams of hydrogen, and last but not least, 35.52% of 100 is 35.52 grams. So mathematically, all you're doing is basically dropping the percent symbol and changing it to grams. Okay, by assuming that we have 100 grams, they are the same thing. Okay, so we did percent to grams, check. We're going to do grams to moles. We have grams of each element, but I need to know how many moles because this is a ratio of how many atoms I have of each element, and we can't compare them by their mass because carbon is a lot heavier than hydrogen, which is a lot lighter than oxygen. So to compare the relative amounts of each thing, we have to change it to how many we have, which is the moles. So I'm going to put each of these over 1. And remember to go from grams down to moles. What we do is divide by the molar mass. Divide by the molar mass of each element. Okay, so divide by the mass of carbon, that's 12.01 grams of carbon in 1 mole of carbon. Then I have the mass of hydrogen is 1.01 grams in 1 mole of hydrogen. And last but not least, oxygen can be rounded to 16.00 grams in 1 mole of oxygen. Okay, so mathematically, if I do all of these divisions, I'm going to get what we already have over here. So for this one, it is 4.996 moles of carbon. This one is going to be 4.44 moles of hydrogen. And oxygen is 2.220 moles. Okay, you guys can see the relationship between these two. This is a 1-to-2 ratio of oxygen to hydrogen. This is going to complicate things a little bit. So we have changed percent to grams, check. Grams to moles, check. Divide all of them by the smallest number. Well, that would be this one right here. Okay, so this is our small. So I'm going to divide each of them by 2.22. Okay, 2, and divide by 2.22, and that's going to give me 2 here. And my 2's aren't coming out. This one is the number divided by itself, so this is going to be 1. And then this one, I said, it's going to be tricky. We get 2.25, almost exactly. Okay, there's some more numbers here, but it's pretty close to 2.25. Now, this is the complicated part. This cannot be rounded to 2. Okay, it's pretty close to 2, but this 0.25 is significant in this example. So what we're going to do is, if the number that we get, the numbers that we get here, are within 0.1 of a whole number, so within 0.1, I'm going to put 0.1 of a whole number, then you're going to round it to that whole number. Okay, so it's safe to round. So in other words, if I had got 2.9, then I can safely round it to 3. If I had got 1.9, then I can round it to 2. Or even 2.1 could have been rounded to 2. But I don't. This is not within 0.1 of a whole number. So what I have to do is change this decimal to a fraction. And you guys should know 0.25 is 1/4. Okay, so I'm going to change the decimal, if it's not within 0.1 of a whole number, to a fraction, and then I have to get rid of it, because what this is saying is my ratio of carbon would be 2 1/4 to 2 to 1. Okay, and we can't have this 1/4 in our ratio. So if I multiply all of them by the denominator, which is 4, I'm going to get rid of that, and I will still have the same ratio. It's like if you have a 1-to-2 ratio and you multiply them by 4, 4 to 8 is the same ratio of things. Okay, we haven't really changed it since we're doing it to both. So we're going to multiply all of these by 4. So times 4, times 4, and times 4, and that's where we get our final answer from. So we get 9, 8, and 4, and that's where our final empirical formula is C9H8O4. Okay, and yeah, that's what we got. So that's how we get to the empirical formula from percentages. Okay, now here are other possible fractions that you might see after when you divide by the smallest number. You might get a 0.2, which would be 1/5. So to get rid of that fraction of 1/5, you'd multiply all of your numbers by 5, and the fraction should go away. We already saw 0.25. We changed it to a 1/4. We multiplied by 4 to get rid of it. 0.33 is equivalent to 1/3 as a fraction, so we would multiply them all by 3 to get rid of it. 0.4 is 2/5, so we're going to multiply by 5. 0.5 is half, so we'll multiply them all by 2. 0.66 is 2/3, so we multiply by the denominator of 3. And 0.75 is 3/4, so we're going to multiply them all by 4. So this is just an example of decimals you might see that are not within 0.1 of a whole number that you would have to change to this fraction, and then you'd have to multiply by this number to get rid of that ratio. Okay, sorry, to get rid of the fraction. Let's do a practice problem. So you guys go ahead and try this. All right, for practice 3.18 out of your textbook, and the answer is in the back as well, by the way, we're going to find the composition of ibuprofen. Okay, so what is the empirical formula of ibuprofen? We have 75.69% carbon. I'm just going to go ahead and change that to grams. 75.69 grams of carbon. Then we have our hydrogen, 8.80 grams of hydrogen. And lastly, we have 15.51 grams of oxygen. Okay, so I changed percent to grams. Now we go grams to moles. Percent to grams, grams to moles, divide by small, multiply till whole. So percent to grams, now we're doing grams to moles. We're going to divide them all by the grams, which is the molar mass in 1 mole. Okay, so the molar mass of carbon, 12.01. The molar mass of hydrogen is 1.01. Oxygen is 16.00. Excuse me. All right, so I got my calculator handy. 75.69. I'm going to try not to make any mathematical errors this time. 12.01. And I get 6.3. The more decimal places you have here, the better your ratios are going to be. So it's 0 to 2. And let's do 8.8 divided by 1.01. And I get 8.7129 moles of C, moles of H, and then 15.51 divided by 16 is going to be close to 1. 0.9694 moles of oxygen. So I did percent to grams, grams to moles, divide by small, that's this one. Divide them all by the smallest. Okay, and let's see what we get. So this divided by itself is going to be 1. 6.3022 divided by 0.9694. 6.5. And 8.7129 divided by 0.9694. 8.99. So this is close enough to round to 9. Okay, I'm just going to put approximately 9. So we have a 1 to 9 to a 6.5 ratio here. So this 0.5 can't be rounded. Since it's 1/2, we have to double everything. So we're going to multiply by the denominator of 2. So that's 13 times 2, times 2, and times 2. So C is going to be 13, H is going to be 18, and O is going to be 2. So this is our final answer for the empirical formula of ibuprofen. Okay, determining the molecular formula of compounds. We've been finding the empirical formula, which is the simplified version of the formula. So remember, for let's say acetic acid, CH3COOH, the shorthand, this is the structural formula right here. It's telling us the structure. The other way of writing it is C2H4O2. This is the molecular formula. That's the actual formula of the molecule. The empirical formula is going to be the reduced version. So CH2O. When I divide these all by 2, I get the empirical formula. So what we're finding here, this is the empirical formula. And what we're going to see is that sometimes the empirical formula is the molecular formula. A good example of that would be water. H2O is the molecular formula of water, but it can't be reduced, so it's also the empirical formula. Okay, so let's look at our problem over here. We can find the molecular formula of a compound from the empirical formula if we also know the molar mass of the compound. This problem didn't give us that, but now they're going to. Example, from the last problem, we found the empirical formula of ibuprofen is C13H18O2. If we were told the molar mass of ibuprofen is 206.29 grams per mole, then we can figure out its molecular formula. I just need to know how much does each of these weigh. So I'm going to add up my 13 times 12.01 plus my 18 times 1.01. These are the molar masses that I'm adding up. And 2 oxygens is 2 times 16. That's a 0. Add that all up, and we get 206.31. 206.31. So that is the molar mass, grams per mole, of the empirical formula. And the problem told us that the molar mass of the actual ibuprofen is 206.29. So if the empirical formula weighs 206, and these are close enough, by the way, to be the same thing. So if the molecular mass is 206 and the molar mass of our empirical formula is 206, these are the same thing. So this is not only the empirical formula, it is also the molecular formula. So the empirical formula and the molecular formula are both C13H18O2. Okay, let's look at one that's not the case. So let's say we did a whole bunch of work and we found the empirical formula for of fructose. Okay, and fructose is a carbohydrate, it's a sugar, so its empirical formula is CH2O. I'm just going to put EMP for empirical. That's the empirical formula of fructose, and it tells us the molar mass of fructose. Molar mass is equal to 180.18, and it wants to know what is the molecular formula. Okay, what is the molecular formula? So how many of these are in this mass? We need to know what the mass of one of these is. So I've added it up over here. I have 12.01 from the carbon, right there, 2.02 from the hydrogens, and 16 from the oxygen. So the molar mass of this guy, molar mass of the empirical formula, is 30.03 grams per mole. So our job is to figure out how many of these are in the total, and we can divide to figure that out. 180.18 grams per mole divided by 30.03 grams per mole. And if I do that, I'm going to find 6 is my answer. So there are 6 of these empirical formulas in the actual molar mass. So all of the subscripts have to be multiplied by 6. So the actual molecular formula is C6H12O6. All right. Okay. And let's do the for practice 3.19. A compound has the empirical formula CH, so just one carbon, one hydrogen. That's called a hydrocarbon. And the molar mass is 78.11. What is the molecular formula? So they did all the hard work for us. Instead of us having to find the empirical formula by doing all of that percent to grams, grams to moles, divide by small, multiply to whole, they tell us what it is. It's CH. And they're telling us that that's the empirical formula. I'm just going to put empirical. And the molar mass, molar mass is 78.11 grams per mole. And how many of these are in that? Well, definitely more than one, because carbon is 12.01 plus the hydrogen is 1.01. So I get 13.02. How many of these are in this 78? You can add them up, so 13 and 13 is 26, and keep going, or we can just take 78.11 and divide it by 13.02, and I get, I hid my calculator from myself. There it is. Sorry about that, guys. This is where I would have you guys calculate it for me. 13.02, 5.99. Which is extremely close to 6. So there are 6 of these CHs in the total. So that means my formula is C6H6. Okay. All right, which is, I believe, benzene. Okay, so last but not least, combustion analysis is a cousin of what we were just doing, the empirical formulas. So what combustion analysis is, another common way to determine the empirical formula of a compound is combustion analysis. A substance undergoes combustion, which means burning, in pure oxygen. The result is carbon dioxide and water, which is weighed, and then we're using the carbon dioxide and the water to find the empirical formula. So no percentages in this one. We just have CO2 and H2O, and there's more steps. So we're going to convert CO2 and H2O to figure out how much, we have grams of CO2 and grams of H2O. We have to change it to moles of CO2 and moles of H2O. So that's the first step, is to go grams to moles. And then we have to break it down farther, because the oxygen didn't come from our mystery compound. The oxygen came from the air. See, they're pumping it in right here. Oxygen's added. So we have to take it from CO2 to just figure out how much carbon was in that compound. And we have to take it from H2O to figure out just how much hydrogen it started with, without the oxygen that came from the air. And then the third step, you only need sometimes. It says use subtraction to find the mass and the moles of any other elements present. Okay, so if there is more than just C's and H's, your life is a little bit harder. You have a few more steps. We have to find how many grams of that mystery. So it's usually like oxygen or nitrogen. We have to find how many grams of that there was, since it doesn't convert to CO2 or H2O. And then we're going to do the same steps that we did before. Divide by small, multiply till whole. Okay, let's look at an example. All right, so combustion analysis of a compound containing only carbon and hydrogen, so that's nice. Just C and H, and we have to figure out what the subscripts are here, how many of each we have in our empirical formula. And it says that we get 1.83 grams of carbon dioxide and 0.901 grams of H2O. Find the empirical formula of the compound. So I'm going to start with my given of 1.83 grams of CO2 over 1. And we can't do much with grams, so we know we're going to change that to moles. This time, since it's grams of CO2 and moles of CO2, the mass is a little bit bigger. It's going to be 44.01. That's a close one. Okay. And we're going to write our 0.901 grams of H2O. And I have to change that to moles of H2O. So divide by the molar mass of water, 18.02 grams in 1 mole of H2O. And I get, I have 0.416 moles of CO2 and 0.0500 moles of H2O. Okay, so that is just one step, sadly. Now we have to change it from CO2 to just C and H2O to just H. So I'm going to rewrite down here, 0.416 moles of CO2 over 1. And this is just a mole ratio. In 1 mole of CO2, there's 1 mole of carbon atoms, because each CO2 has that 1 carbon atom. Okay, so this is a 1-to-1 ratio. So it's just going to be 0.416 moles of C. And then let's do the water. The water is 0.0, I keep forgetting that first 0. 500 moles of H2O. And this one is slightly tricky, so don't mess this up. We have 1 mole of H2O on the bottom. How many moles of hydrogen are in each mole of water? Well, every water molecule has 2 hydrogens attached to it. So if I have a whole mole, like if I had a dozen of these water molecules, I would have 2 dozen hydrogen atoms. So there are 2 moles of H for every 1 mole of H2O. So I need to double that, and doubling this makes it 0.1 moles of H. So now I can look at the ratio of hydrogen and carbon right here. And that is our, that's going to be our subscript. So to figure out the ratio, I divide by small. That's this one. Divide them both by point. Oh, I missed a 0. I'm sure you guys caught that. Good job. I'm so glad I got that before I finished the answer there. Okay, so it's 0.04. So this is my small. Okay, which is going to be 1. And 0.1 divided by 0.0416 is going to be 2.4. Okay, and if you remember, 0.4 is 2/5. So I have 2 and 2/5 to 1. And so I cannot have a 1 to 2 and 2/5 ratio. I need to multiply both by 5. And I get C5H12. This is my empirical formula, and that is pentane. Okay. Right. All right, so combustion analysis. This one is a doozy. This is the whole enchilada where we have the carbon, hydrogen, and we have oxygen now in our mystery compound. So we are burning a compound containing C, H, and O. So we have C, H, and O, and let's call it X, Y, and Z. We're trying to figure out what those subscripts would be. We are given 2.445 grams of CO2, and we are given 0.6003 grams of H2O as our starting point. So when they burned the sample, this is what the carbon dioxide and water they got out was. Okay, so remember, our first step is change it from grams to moles. Grams of CO2, 1 mole of CO2. Remember, our mass was 44.01. Over here, grams of H2O, 1 mole of H2O, and it's 18.02. Okay, so if I have what did I do over here? I put the mass of the sample instead of the mass of the, okay, let's recalculate over here, and hopefully I have the right answer because this was in the textbook on page 118, by the way. So I'm going to use my calculator, and I'm going to hit 2.445, which is the actual mass of carbon dioxide, and divide it by 44.01. And I do get this value. So even though I wrote the wrong thing here, ignore that. This is the correct answer. So I have 0.055, and it keeps going, 6 moles of CO2. And down here, I'm going to have 0.03331 moles of H2O. Okay. And I still have to figure out how much oxygen. Okay, so this is the tricky part. I know the total mass of my sample, is my 0.8233 grams. Okay, so this is the total. It tells us upon combustion of this much sample, you get this much carbon dioxide and this much water out. So this sample contains C's, H's, and O's, okay, from what was given off. We know, or we will know, how much C and how much H we have, so we can subtract the mass of carbon and hydrogen from the total, and the leftover will be the mass of the oxygen. Okay, so here's our full sample. I'm going to draw it as a tape because I've been working with tapes with my daughter. Okay, so let's say I have carbon takes up this much, hydrogen takes up this much. The whole thing is my 0.823. So to figure out what's left, I'm just going to take this total, and subtract the C and the H's, and I'll have the amount of oxygen that's left. Okay, so a few more steps to do. We need to change from the moles of CO2. So from this mole of CO2, I need to change it to just carbon. I'm going to do it right here. I'm going to squeeze it in. So 1 mole of CO2 is 1 mole of C. And down here, 1 mole of H2O is 2 moles of H. Okay, remember that. So this is just our same answer, 0.055, and there's a 6 down there. And this is going to be double that, so it's 0.06662. Okay, you guys get the idea here. It's over here as well, if you're getting confused. Okay, so I have the moles of carbon and hydrogen. So here's the extra steps. I have 0.0 moles of carbon right here, 0.05556 moles of carbon. I need to kind of backtrack and figure out how many grams of carbon I had to figure out this number. So 1 mole of carbon is 12.01 grams. Okay, and that is going to be 0.6673 grams of carbon. And then I had my 0.662 moles of H2O. Moles of H over 1. And I want to change that to from 1 mole of H to the grams of H. So that's going to be pretty close to the same number, 0.06715 grams of H. So I'm going to take my, I'm going to take my 0.8233, which is the total mass, minus the mass of carbon, minus the mass of hydrogen, and what's left over, remember, is my mass of oxygen. Let me scroll down a little bit. Okay, so I'm going to get equals 0.0889 grams of O. Okay, so I'm going to compare my moles of oxygen to my moles of hydrogen to my moles of carbon, and I'm going to rewrite it down here because it's getting kind of messy. So right now we have grams of oxygen, 0.0889 grams of oxygen over 16 grams of O in 1 mole. That's supposed to be 16.00. You guys get the idea. And I have 0.00556 moles of oxygen. Okay, so this is my O. From back up here, I'm going to rewrite the C and the H. So the C, let's scroll back up. Where was moles of C? Moles of C is way over here. It's 0.055. Okay, so I had 0.05556 moles of carbon, and my hydrogen, I had 0.0662 moles of hydrogen. So all of that work was to get moles of carbon, moles of hydrogen, and then last but not least, moles of oxygen. Okay, so we are at our last step, divide by small, multiply till whole. This is the smallest number. It's very close to this number, but you can see that it has one more decimal place. So this is the smallest, so let's divide them all by 0.00556. That's going to take us to 1 divided by 0.00556, and that is going to be 12. And this divided by 0.00556, that is going to be 10. Okay, because this is 10 times smaller. So 10 to 12 to 1, and our final answer we are done is C10, H12O1, which we don't write the 1. That is our empirical formula using combustion analysis, and that was a lot of work. All right, guys, have a great day.